March 14, 1945. A lone Avro Lancaster taxis onto a Lincolnshire runway, riding so low that ground crews worry the tires might burst before takeoff. Suspended in its belly is a bomb heavier than some fighters, 22,000 lb of hardened steel and Torpex. Squadron leader C.C. Calder knows what he carries, a weapon 5 American B-17 flying fortresses couldn't lift. This isn't national bragging. It's engineering and arithmetic. Britain and America approached the bomber war differently. The Lancaster didn't merely carry more, it occupied a different class of payload capacity. Where American crews measured effectiveness in numbers and area, the B-17G, the common type over Germany in 1945, could lug at most 8,000 lb on short hops. On deep raids that figure fell to about 4,000, 6,000, because fuel mattered. Do the sums, 5 B-17s could theoretically deliver 20,000 to 30,000 lb. But maths hides an important truth. Those loads would be dispersed, jettisoned from 5 separate aircraft from different release points, scattering impact zones across hundreds of feet. The Lancaster could concentrate 22,000 lb onto a single aim point. One aircraft, one bomb, one target. That concentration changed what strategic bombing could achieve. Many German structures weren't vulnerable to carpet bombing, not for lack of explosive force, but for lack of concentrated force. Submarine pens with 23 reinforced concrete roofs. Prussian-built viaducts with massive stone arches that had withstood a century of weather. Underground factories carved into mountainsides. Dropping 1/500 lb bombs might crinkle the surface and cost aircrew lives without crippling such targets. Here the Lancaster's unique role mattered. It wasn't built to do what 5 B-17s did. It was designed to do what 5 B-17s could not, even in theory. It could carry weapons that rewrote aerial bombardment's rules. By March 1945, it bore the Grand Slam, a munition Barnes Wallis had sketched before the war but could not build because no aircraft then could lift it. The Lancaster made the impossible real, and in doing so altered the final months of the European war in ways official histories sometimes underplay. Wallis did not begin with a bomb. He began with a problem: how to destroy things engineered to survive direct hits. His answer inverted bombing theory. Rather than blasting through defenses, he aimed below them. The earthquake bomb concept. Drop a mine-heavy bomb from great height, ideally 40,000 ft, so gravity and streamlining turn it into a supersonic projectile. It would not detonate on impact, but penetrate soil, clay, and rock like a bullet in water, burrowing deep before exploding. Detonated 9,100 ft underground, the blast behaved less like a surface explosion and more like a localized quake. The ground heaved, foundations cracked, and buildings engineered against surface blasts collapsed from beneath because their designers had never planned for an attack from below. Wallis first tested his idea on paper, borrowing math from seismology, mining engineering, and ballistics. The result demanded a monstrous bomb, far heavier than the Allied arsenal then contained. Long and streamlined, with a hardened casing to survive impacts that would shatter ordinary munitions, and filled with Torpex, a British explosive about 50% more powerful than TNT, already proven in naval mines and depth charges. By 1941, Wallis had formal specifications. A 22,000 lb weapon, some 26 ft long, needing an aircraft that did not yet exist. The Air Ministry shelved it, not for lack of theory, but because no Allied bomber in 1941 could shoulder such a load. The heaviest bombs then were 2,000 lb. 4-engine heavies like the Short Stirling and Handley Page Halifax were still maturing. Undeterred, Wallis scaled down the tall boy. At 12,000 lb was still enormous by 1942 standards, but feasible if the right aircraft were modified. The Tallboy entered operational service in June 1944, and it proved Barnes Wallis's theory beyond argument. Dropped on the Saumur railway tunnel in France, a single Tallboy bored 60 feet through earth and rock before detonating. collapsing the tunnel and trapping an entire German panzer division racing toward the Normandy beaches. The Air Ministry took notice. If a 12,000-pound bomb could do that, what might 22,000 accomplish? By late 1944, Wallis finally had both his aircraft, the Lancaster, and the production capacity to build the weapon he'd imagined 5 years earlier. The Grand Slam was no longer theory. It was real, and it was terrifying. The B-17 Flying Fortress was no failure. It was a triumph of American engineering, but it had been designed for an entirely different mission profile, and that design imposed limits that even the best engineers couldn't erase. When Boeing conceived the B-17 in the late 1930s, it was meant for precision daylight bombing from high altitude. The logic was straightforward. Fly above most flak, use the Norden bomb site to hit industrial targets, and rely on defensive firepower, 13 50 caliber Brownings, to fend off fighters. Every feature of the B-17 served that concept, and every feature also made it incapable of lifting super-heavy ordnance. Start with the bomb bay. The B-17's internal bay was about 11 feet long and just over 3 feet wide, split into 2 sections by a central structural beam carrying the wing loads. That wasn't a mistake. It was essential for keeping the wings attached during stress and landings. Remove it and you cripple the airframe. The divided bay suited its intended racks of 500 or 1,000-pound general-purpose bombs perfectly, but set an unbreakable ceiling on bomb size. The largest single weapon it could hold internally was a 2,000-pounder, and even that required stripping racks. Then came weight. The B-17G's maximum takeoff weight was about 65,500 pounds. Subtract roughly 36,500 for the airframe, leaving some 29,000 for everything else: fuel, crew, ammunition, and bombs. A Berlin range mission demanded about 2,800 gallons of fuel, roughly 17,000 pounds. Add 10 crew with gear, oxygen, and gun ammunition, and the practical bomb load shrank fast. The 8,000 pounds quoted in manuals existed only on paper and only for short hops. In combat over Germany, most B-17s carried 4,000, 6,000 pounds, because anything more meant not coming home. American bombing doctrine didn't see that as a flaw. It was the strategy. The USAF believed mass formations could saturate a target area with hundreds of smaller bombs, ensuring that something vital would be hit. One B-17 couldn't erase a ball-bearing plant, but 300 dropping 200 tons could flatten an entire industrial district. It worked for cities, rail yards, and factory zones, but failed utterly against hardened point targets like submarine pens, vast viaducts, or underground bunkers that demanded penetration and concentrated explosive force. The B-17 could never carry a Grand Slam. The bomb was 26 feet long, twice the length of its bay, and nearly 3 times its normal load, more than half the plane's total payload including fuel. No modification could fix that. The Lancaster existed because Britain had gambled in 1940 that bigger was better and accepted sacrifices to achieve it. When Avro's team under Roy Chadwick designed what became the Lancaster, their aim wasn't to match the B-17, it was to outcarry it threefold. The result was a 4-engine heavy bomber built around a single overriding priority: maximum bomb capacity with maximum flexibility. Everything else, defensive guns, crew comfort, range, came second to the question of how much destructive power could be hung beneath the wings and delivered in one go. Its defining feature was the bomb bay, 33 feet long, uninterrupted from behind the cockpit, well past the wings. No central beam, no obstruction, just a cavernous void capable of swallowing weapons the rest of the world considered too large to fly. In standard trim, it could haul 14,000 pounds, already more than the B-17's theoretical best. But Chadwick and his engineers weren't done yet. They knew that figure was only the beginning. The engineers designed the bomb bay doors to be removable and replaceable with bulged fairings that extended downward, creating even greater internal space. With this bulged bay modification installed, the Lancaster could carry weapons up to 33 feet long and loads that seemed aerodynamically impossible. The structural design required to make this feasible was extraordinary. The fuselage employed a geodetic-inspired framework with massive load-bearing longerons running the aircraft's length. The wings attached to a central structural node that spread the stresses across multiple points rather than a single spar. This allowed the aircraft to endure asymmetric loads and radical shifts in its center of gravity that would have torn other bombers apart. When a 22,000-pound Grand Slam hung beneath a Lancaster, its balance shifted sharply aft and downward. The landing gear sagged under the strain, but the airframe held because it had been engineered from the outset for exactly such extremes. Power was the other essential factor. The Lancaster relied on 4 Rolls-Royce Merlin engines, the same legendary power plants that had made the Spitfire famous. In the bomber, they were Merlin XX or 24 variants, each delivering roughly 280 horsepower. Together, they produced about 5,120 horsepower, enough to lift a maximum takeoff weight near 72,000 pounds. Fully loaded with a Grand Slam, the Lancaster often exceeded 70,000 pounds, pushing the very limits of what its engines and frame could bear. Takeoff runs lengthened and climb. Rate dropped to barely 200 feet per minute, but the bomber flew, and that was what mattered. The Grand Slam modifications went well beyond the bomb bay. The mid-upper turret was removed to save weight and drag. Armor plating protecting the crew was stripped out. Some missions even flew with reduced fuel, trading range for the privilege of carrying that massive bomb. These compromises were ones the Americans would never have accepted. The USAAF prized crew safety and defensive power, but by 1945, Britain was fighting under different constraints. The war's end was near, but some targets remained untouched by conventional means. The Lancaster, fitted with its bulged bay, gave Bomber Command a singular capability to deliver an unprecedented weapon onto one precise point. By March 1945, fewer than 30 Lancasters had been modified for Grand Slam operations. They belonged to No. 617 Squadron, the famed dambusters, now flying missions ordinary bomber crews could scarcely imagine. The Bielefeld Viaduct had become a symbol of German engineering stubbornness and Allied exasperation alike. Built between 1845 and 1847, the immense railway bridge carried the main line between Hamm and Hanover across the Johannisbach Valley in northwest Germany. Its 23 stone arches, each 50 feet high, had been crafted by Prussian engineers for permanence. By March 1945, it had endured 54 bombing raids. The RAF had dropped more than 3,500 tons of bombs on it. American B-17s and B-24s had added their share. The surrounding countryside was cratered. Rails had been hit and repaired countless times, but the viaduct's arches still stood, still bearing trains to the front. This wasn't about a single bridge anymore. The Bielefeld Viaduct embodied everything wrong with conventional strategic bombing against hardened infrastructure. You could hit near it, around it, even on it, but to destroy 19th-century masonry with 3-foot-thick arches demanded something conventional explosives couldn't offer: concentrated, penetrating force at a single point. The arch's geometry distributed weight so efficiently that even direct hits with 2,000-pound bombs only chipped stone. The bridge was simply too massive, too well designed, too fundamentally solid for surface blasts to break. The 617 Squadron received its orders on March 13, 1945. 1 Lancaster, 1 Grand Slam, 1 target. Squadron leader C.C. Calder would command the modified bomber carrying the earthquake bomb. The mission profile broke nearly every rule of Bomber Command procedure. The Lancaster would fly alone, no formation, no fighter escort for most of the route. It would climb to 20,000 feet above the target, far higher than standard precision raids, because the Grand Slam needed altitude to reach its terminal velocity. Bombing would be visual in daylight, using the advanced Mark 15 bomb sight. Every aspect of the plan defied doctrine, but doctrine had failed 54 times already. March 14th dawned with clear skies over Lincolnshire, rare fortune for a precision strike. Calder's Lancaster lifted off from RAF Woodhall Spa at 09:45 hours, straining along the runway, its 22,000-pound payload dragging it down. The climb to altitude took 45 minutes, the 4 Merlins roaring at full power to lift the overloaded machine. By the time they crossed into German airspace, the bomber was utterly alone, too heavy to maneuver sharply if intercepted. But by March 1945, the Luftwaffe's fighter strength was spent. Most of the Luftwaffe's surviving fighters sat idle for lack of fuel, and the Lancaster flew on unchallenged. At 12:47 hours, the Bielefeld Viaduct came into view. Calder steadied the bomber at 20,000 feet while the bomb aimer locked the Mark 15 sight on target. Beneath the aircraft, the Grand Slam hung exposed, its 4 stabilizing fins glinting in the sunlight. At 12:49, the bomb released. For an instant, it vanished so fast, it seemed to blink out of existence. Then came the waiting. A Grand Slam dropped from 20,000 feet takes about 40 seconds to fall. Calder banked the Lancaster sharply to escape the blast zone. Unsure what would happen, no one had ever dropped one on a bridge. The weapon struck 30 feet from the viaduct's base, boring deep into the soil before detonating. The explosion was nothing like the fiery plumes of conventional bombs. Instead came a heaving shock that rippled through the ground itself. 2 great stone arches collapsed at once, their foundations shattered by forces traveling upward through the earth. A 200-foot section of the viaduct plunged into the valley. What occurred beneath Bielefeld in those fractions of a second explains why the Grand Slam succeeded where thousands of tons of bombs had failed. This wasn't merely about explosive power, it was about physics, timing, and the behavior of shockwaves in solid matter. When a typical 1,000-pound bomb detonates on the surface, roughly 95% of its energy vents into the air. You get blast, heat, and flying fragments, devastating for buildings or rail yards, nearly useless against deep, stone-built structures. The Grand Slam obeyed different laws. From the instant it fell from the Lancaster, gravity and aerodynamics transformed it into a kinetic weapon before it ever exploded. Its teardrop shape and hardened nose reduced drag and maximized speed. By impact, it was traveling at around 750 miles per hour, just below the speed of sound. At that velocity, 22,000 pounds of steel and torpex carried kinetic energy measured in millions of foot-pounds. It didn't just fall, it drove itself into the earth like a meteor. The forged one-piece steel casing was vital. Wallis had specified walls thick enough to survive the kind of impact that would pulverize cast iron or standard bombshells. On striking soil, clay, or rock at near supersonic speed, the nose deformed slightly but held, turning the bomb into a self-burrowing projectile. Its momentum carried it far deeper than any other weapon. Wartime and post-war analyses showed average penetration between 90 and 130 feet, depending on terrain. At Bielefeld, geological data suggested about 95 feet before the fuse triggered. Then the earthquake effect began. When 135 pounds of torpex detonated nearly 100 feet underground, the blast could only travel through solid earth. Unlike air, which absorbs energy, soil and rock, transmit it brutally well. The detonation sent out 2 kinds of seismic energy, rolling surface waves and compression waves moving through the subsoil. Together, they mimicked an earthquake of magnitude 4.0 to 4.5 on the Richter scale, but concentrated within a few hundred yards. The viaduct's 1840s arches had been built to bear downward weight, locomotives, freight and wind stresses, not vertical acceleration from below. When the seismic surge hit the foundations, the structure was thrown upward, then dropped as the ground heaved. The arches tried to flex but couldn't. Rigid stone cracked where it had once endured a century of strain. Mortar joints failed, and the precision of Prussian masonry turned against itself. Then came the camouflage effect, the formation and collapse of the underground cavity created by the blast. The Grand Slam vaporized everything within 40 feet of the detonation point, leaving a spherical void. As the pressure subsided, that void partially caved in, causing secondary tremors that continued for several seconds. Foundations that had survived the initial shock suddenly hung over empty space and gave way. Eyewitnesses later described the bridge not as exploding, but as melting into the valley, sagging and crumbling as though the ground had liquefied beneath it. The core difference between British and American heavy bombing wasn't about who built better planes. It was about two irreconcilable philosophies of air warfare. 5 B-17s could blanket a target, one Lancaster could erase it. Carrying a Grand Slam was never just a question of payload capacity. It represented two entirely different philosophies of destruction, two approaches to risk, precision, and the use of concentrated force, and two competing answers to what strategic bombing was meant to achieve. 5 B-17s on a 1945 mission might together deliver 20,000 to 25,000 pounds of ordnance, roughly equal in weight to a single Grand Slam, but those bombs would be dispersed across 5 aircraft flying in formation. Separated by 300 to 500 feet, each bombardier worked independently with his Norden bomb sight, aiming as best he could, knowing that bombing accurately from 25,000 feet was as much luck as science. Even under ideal conditions, the circular error probable, the radius within which half the bombs would land, was about 1,000 feet. In practice, those 5 B-17s were carpet bombing a quarter-mile circle and hoping the target was somewhere inside. Distribution was everything. Those 20,000 pounds weren't uniform. They might include a mix of 500 and 1,000-pound general-purpose bombs, with perhaps a few incendiaries depending on the target. Each would explode on or near the surface, carving its own crater and sending up its own shockwave. Against soft targets, wooden structures, train yards, or city blocks, this method worked brilliantly. The area within that quarter-mile would be obliterated. But against a hardened point target, a viaduct, submarine pen, or buried bunker, the same tonnage achieved little more than scattered pockmarks and wasted effort. It was like throwing handfuls of gravel at a wall instead of swinging a sledgehammer at one spot. The Lancaster, with its Grand Slam, was that sledgehammer. One aircraft, one aim point, and by 1945, the specialized crews of 617 Squadron were routinely achieving accuracy within 300 feet from 20,000 feet altitude. More importantly, all 22,000 pounds of energy hit one place and burrowed deep underground. The destructive mechanism wasn't surface blast, but seismic shock and foundation collapse. The idea wasn't to blow the structure apart from without, but to make the ground itself convulse until the structure failed from below. Risk was another dividing line. 5 B-17s meant 50 men in the air. Losing one to flak or fighters cost 10 lives, but the mission continued. American doctrine spread risk across massed formations, trusting that numbers would overwhelm defenses. A Grand Slam sortie, by contrast, placed all bets on one plane, 7 men, 1 bomb, 1 chance. If flak, fighters, or engine failure brought it down, the mission and its irreplaceable weapon were gone. Yet by spring 1945, German defenses were too weak to stop such lone intruders, and the RAF was willing to trade risk for the ability to destroy what conventional bombing could not. Cost added another layer of logic. A Grand Slam cost about $4,000 to make, expensive by wartime British standards, roughly the earnings of a skilled worker for several months. But compare that to the cost of hundreds of sorties against indestructible targets. The Bielefeld Viaduct alone had endured 54 separate attacks. How many aircraft bombs and aircrew lives had been spent before one Grand Slam finally erased it? Measured against operational cost, the earthquake bomb proved economical, precisely because it could accomplish in one strike what massed formations might never achieve at all. The Grand Slam's active service was brief. Only 41 were dropped between March and May 1945, but its legacy echoed far beyond those few missions. When Allied investigators surveyed post-war Germany, they studied the results at Bielefeld, Arnsberg, and the Valentin submarine pen. Their findings reshaped military thinking about how to defeat hardened targets. Wallis's theory demonstrated that penetration depth mattered more than sheer explosive yield. That lesson outlived the Lancaster, feeding directly into Cold War weapons design and eventually the precision-guided munitions that define modern warfare. The U.S. Army Air Forces, once skeptical of super-heavy bombs, changed course almost immediately. In 1946, American engineers dissected the Grand Slam's construction and pored over RAF strike reports. Their work produced the T-12 Cloudmaker, a 43,600-pound American earthquake bomb that pushed Wallis's idea even further. The T-12 never flew in combat, too late for World War II, unused in Korea. But its creation proved the point. The United States had absorbed the British lesson in how to break the unbreakable. The lessons Britain demonstrated were clear. Some targets required specialist weapons, and occasionally a single massive penetrating bomb could achieve what 100 conventional ones could not. Cold War bunker-busting arms descended directly from Wallis's earthquake bombs. NATO planners, facing Soviet command bunkers and missile silos topped by 20-30 feet of reinforced concrete and buried under rock and soil, understood that ordinary iron bombs were ineffective. The solution was deep, penetrating munitions that could either pierce the overhead protection or, as the Grand Slam did, bypass it by striking through the ground. America's later Blue 109 bunker buster, fielded in the 1980s, used a hardened steel casing and special fusing to break concrete before detonation, exactly the approach Wallis pioneered 4 decades earlier. Precision-guided weapons extended the idea further by combining penetration with accuracy. The GBU-28, developed during the 1991 Gulf War to attack Iraqi command bunkers, weighed about 5,000 lb and could cut through over 20 ft of concrete or some 100 ft of earth. The GBU-57 Massive, ordnance penetrator, introduced in 2011 at roughly 30,000 lb, was designed to reach deeply buried facilities no prior conventional weapon could touch. These modern penetrators trace a direct line back to the Grand Slam, make the warhead heavy enough, hard enough, and accurate enough, and previously invulnerable targets become vulnerable. The Lancaster's capability also shaped post-war bomber design thinking, particularly in Britain. Avro's Vulcan, one of the V-bombers that carried nuclear weapons during the Cold War, inherited the Lancaster's emphasis on payload flexibility rather than heavy defensive armament. The Vulcan carried few guns, but a cavernous bay able to accept a broad range of weapons, from nuclear gravity bombs to conventional loads and, later, anti-ship missiles. That design choice, prioritize what you can carry over how you defend yourself, flowed straight from Lancaster experience. Perhaps the most enduring legacy is doctrinal. The Lancaster and the Grand Slam proved that some problems demand bespoke solutions, not merely larger quantities of existing munitions. Modern air forces therefore keep specialized arsenals for specialized missions, bunker busters for fortified facilities, thermobaric systems for cave networks, and penetrating warheads for subterranean tunnels. One right weapon can do what 1,000 wrong weapons cannot. Today, the Lancaster itself is retired and preserved in museums, where visitors still marvel at the bulged bomb bay that once swallowed ordnance measured in tons rather than pounds. The principle it embodied, that payload capacity and weapon specialization can trump sheer numbers, remains integral to how contemporary militaries conceive air power. The Lancaster could carry what 5 B-17s could not, because it was designed to solve problems the B-17s were never intended to solve. That distinction mattered when it mattered most.